All right, so time to talk about the polar coordinate system. So we know already that if we have a point in space, let's call it xy, the coordinate system that we've been working in already is the Cartesian coordinate system, also known as rectangular coordinate system. Okay, and that's because if you start at the origin, what's the address of that point xy? Well, it's x units this way and y units this way. Okay. However, the polar coordinate system arrives at that point a different way. In the polar coordinate system, what we do is we say it's r units this way and theta units up in standard position. And so we would give these coordinates in r comma theta. All right. Now, unlike Cartesian coordinates, polar coordinates for a given point are not unique. Well, what do we mean by this? Well, let's take a look at a random point. So let's look at this point right here. And in the coordinates, in the polar coordinate form, let's say it's 2 units out and 45 degrees or pi over 4 radians. Okay, so that would be this guy right there. And again, this is the angle here, theta, which is pi over 4 radians. Okay, so now we could also label that as 2 comma, and instead of moving in standard position pi over 4, you could go all the way around 2 pi plus another pi over 4. So we could say, well, this is pi over 4 plus 2 pi. Okay? Or you could say it's, go around a bunch of times. So that's a multiple of 2 pi plus pi over 4 again. So this could be like pi over 4 plus, in fact, any multiple of 2 pi. So I'll just write 2 pi n. We'll get you there. You could even go the opposite direction. So this would be negative 2 pi and then plus pi over 4. All right. But there's more, because we could also get to this point by saying point yourself in this direction, okay, and go negative 2 units. And that would get you to that point. So this point in polar coordinates could also be given as negative 2, comma, and then that would be 5 pi over 4. Okay, so 5 pi over 4, again, is pointing in that direction into the third quadrant, and then it's like you're stepping backward because you're going negative 2 units, and that lands you right at the point we're interested in. Okay, and you could also add 2 pi to that. So we could go 5 pi over 4, and just for fun, go around the unit circle one more time. Okay, so, all right, well, how do we catch all of these in a nice statement? Well, we could say that r theta, for any theta and any r, can be written as r comma theta plus 2 pi times n, right? That's stipulating that n is an integer. Or we could write it as negative r, and then theta plus an odd multiple of pi. So we could say 2n plus 1 pi. All right. Now the origin, which in polar coordinates is often called a pole, is simply when r is equal to 0. However, the angle at the pole can be anything, right? Because it's like saying, well, how do you get to the origin? Well, point yourself in any direction you like and then stay there. Okay, so yes. So it's denoted 0, comma theta for any theta. However, to not confuse people deliberately, it's a good idea just to use 0, 0, right? Looks like the origin then. All right, well, let's just take a look at this situation here. So if you have a point xy, and it's also r theta, well, geometrically, you can relate all the different measures involved here. So this length is x, that height is y, this hypotenuse or direct distance is r, and then you have an angle theta right there in standard position. So we can see that x is equal to r cosine of theta, and y is equal to r sine of theta. And these are the equations that you would use to convert from polar to Cartesian form. Okay, because it outputs very nicely x and outputs very nicely y if you have r and theta already known. On the other hand, we can also see by the Pythagorean theorem that r squared is equal to x squared plus y squared. And we can also see from trigonometry that tangent of theta is y over x. And we're going to use those ones when converting from Cartesian to polar. All right, so let's look at some examples where we do some conversions. All right, so here are some points in polar form. Let's plot them and then convert them to Cartesian form. That sounds super fun. So first one is 5, 5 pi over 6. Okay, so we're going to locate 5 pi over 6, which we know is about here, this direction. And we're going to go 5 units that way. So that would be about, well, if we can imagine, here's 1 unit out, 2, 3, 4, and 5 units out. Okay, so it's 5 units away from the origin in a direction of 5 pi over 6, which is about this point right here. So there's the 5 pi over 6. All right. And let's convert that guy over to Cartesian. So we'll use those guys. So for part A, it's x will be r is 5 times cosine of 5 pi over 6. So that's 5 times negative rad 3 over 2. Okay, which is negative 5 rad 3 over 2. And our y will be 5 times sine of 5 pi over 6, which is 5 times 1/2, or 5/2. So the xy coordinate will be negative 5 rad 3 over 2, comma 5/2. Okay, and if you look at our plotting of A, that seems reasonable for its xy coordinates. All right, now let's look at B. Okay, so B says move 0 units away from the origin and 64 radians, point yourself in an angle of 64 radians. Well, I have no idea where 64 radians is in terms of direction, but no worries because we are at the pole, the origin here. So that's 0 units away from the origin, pointed at an angle of 64 radians. Fascinating. So now let's do the conversion using the formulas just to practice using them. Let's say we're not quite convinced this is the origin. So x is equal to r cosine theta. That would be 0 times cosine of 64 radians. Oh no, I have no idea what cosine of 64 radians is. No problem. Multiply by 0. Y is 0 times the sine of 64 radians. and that also evaluates to 0. So the xy coordinate will be 0, 0. Of course, in Cartesian system, the only way to represent the origin is 0, 0. All right, and finally, the last point is negative 2 comma 9 pi over 4. So 9 pi over 4 is, well, there's pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5, 6, 7, 8, and 9 pi over 4. So we're good and pointed in this direction, and we're all set to move the number of units that r is, except here r is equal to negative 2, which means we're moving 2 units out. Okay, so there's 1 unit, 2 units. So this would be negative 2, 9 pi over 4. All right, even though the direction 9 pi over 4 is a first quadrant angle, this actual point is in the third quadrant. Okay, and let's see that manifest using the formulas. So x is equal to r cosine theta. That would be negative 2 times cosine of 9 pi over 4. 9 pi over 4 itself, like I said, is a first quadrant angle. So this is going to come out to negative 2 times rad 2 over 2, which actually will just be negative rad 2. And y is going to be negative 2 times sine of 9 pi over 4. And that will also come out to negative of rad 2 altogether, which means the xy coordinate will be negative rad 2, negative rad 2. Okay, and clearly you can see it in the third quadrant when it's written that way. And also, if we go and look at this, if we understand that the square root of 2 is about 1.4, you would agree that negative rad 2 gets you about here and here. And so the coordinates in Cartesian form of negative rad 2 do seem to agree with where we located this point in polar form. Okay. All right, so now we're going to convert Cartesian points to polar form. So we're going to use this set of equations. R squared is x squared plus y squared, and also tangent of theta is equal to y over x. Okay, so let's take a look at part A here, negative 2 and 2 root 3, of course. That's x and y. All right, so we know that r squared is x squared plus y squared, which is negative 2 squared plus 2 root 3 squared. So that would be 4 plus 12, which is 16. Okay. Now, we could choose whether we wanted r to be positive or negative. Let's let r equal plus or minus 4 for a moment. We'll make our decision later. But let's note something, that this point is in quadrant 2. All right, because it's got a negative x value and a positive y value, which means that if we choose r equals 4, then theta must be in quadrant 2. However, if we let r equal negative 4, then theta actually must be in quadrant 4, because theta will point in quadrant 4, and then we're going to move backward the negative r amount, which will get us into quadrant 2. Okay, so we have to be very careful when choosing our theta. Well, let's find theta. Well, we know that tangent of theta is y over x, and y is 2 root 3, and x is negative 2, so this is just negative root 3. Okay, and of course we get to choose quadrant 2 or quadrant 4 for a negative tangent value. So why don't we select the points? Say 4, positive 4, comma, now we choose a quadrant 2 angle whose tangent value is negative rad 3. So that would be, say, 2 pi over 3. Okay. But we could also go with -4 and choose a quadrant 4 angle whose tangent value is -rad3. Okay, so that would be, say, 5 pi over 3. Okay, and by no means are those the only answers. We could have gone with anything coterminal to 2 pi over 3, right? We could have subtracted 2 pi from it and gone -4 pi over 3 and +4. Or we could have subtracted 2 pi from this one and gone -4, 5 pi over 3 minus 2 pi would be -pi over 3. Okay? And, I mean, let's just quickly check that one. -pi over 3 we know reads clockwise from the positive x-axis in standard position. So there's -pi over 3. So we're pointed that way. But we're going -4 units. So our point will be out here somewhere, which is, of course, makes sense. That could be -2, 2, 3 in the second quadrant. All right. So let's look at part B, the point -1, 5. Okay, and again, we're going to just use the fact that we're given x and y here, and so r squared is x squared plus y squared, which is -1 squared plus 5 squared. So that would be 1 plus 25, which is 26. So again, same reasoning as before, we could choose plus or minus rad 26. Okay, we can see here that our point is in quadrant 2, again, just like the last one was, which means that if we choose a positive r value, we need a quadrant 2 angle. Okay, so let's find theta. We know that tangent of theta is y over x, which would be 5 over -1 or -5. Okay, well, -5 is not one of our special ratios for tangent, so we would need to bust out the inverse tangent function to finish this. Okay, no problem, because we know trigonometry. So our answers are going to be, let's start with positive rad 26, okay, which means we must choose a second quadrant angle, and we have no choice but to do something like this, inverse tangent of -5. Question is that in the right quadrant? Well, inverse tangent of -5 has a range of -pi over 2 to +pi over 2, which means that if you input -5 into inverse tangent, it's actually going to produce a fourth quadrant angle. So this is going to be negative some angle, which will be in the fourth quadrant. But we actually need a second quadrant angle because we chose a positive r value. So we need to add pi to our inverse tan of -5. Okay, so there's one answer. If you want to avoid that, you can choose a negative r value, and now we have to go with a fourth quadrant angle, which is naturally generated by inverse tangent of -5. Okay, so those are two perfectly good answers. All right. Now, the next example will be converting full equations back and forth. All right, so now we're going to look at some conversions from polar to Cartesian of equations. So we're still going to appeal to the same little group of formulas. So, all right, so let's look at our first polar equation, which is simply r equals 5. So what we want to do is look at this entire array of formulas here and see how we can use one or more of those to get everything in terms of x and y. And let's just note here that if we square this guy, we can immediately convert r squared to x squared plus y squared. And then we would recognize that this is a circle of radius 5 centered at the origin. Okay? So let's look at part B here. What about if we have the equation r equals 7 secant of theta? Well, we could also square both sides of this guy, all right, giving us an r squared. And once we have an r squared, we have x squared plus y squared. But then we'd be burdened with a secant squared as well. And while that's not a huge problem because we can turn secant squared easily into tangent squared, and then we can turn tangents into y over x, there's a little bit there's something a little bit easier we can do instead if we just start this whole thing over. Notice that r times cosine of theta is equal to x. So if we multiply both sides by cosine of theta, then we simply get r times cosine theta equals 7. And we know that r cosine theta is x, so this is just the vertical line, x equals 7. All right, how about this one? R equals secant theta tangent theta. Well, we can do the same thing. We have a secant, move it over, because that's going to create an r cosine theta. So we have r cosine theta equals tangent of theta. And each of those we know how to convert. R cosine theta is x. Tangent of theta is y over x. And so this is actually the parabola y equal x squared. Okay, what about this one? R equals 2 over 3 cosine theta plus sine theta. All right, well, once again, if you move that denominator over, you'll have r cosine and you'll have r sine, and those easily convert respectively into x and y. All right, so this guy here just becomes 3r cosine theta plus r sine theta is equal to 2. And r cosine is x and r sine is y. So what we have is 3x plus y equals 2. And solving for y, we get y equals negative 3x plus 2. Okay, so that's a line with slope negative 3 and y-intercept 0, 2. So we know everything about that particular polar equation now. All right, let's do one more. What if we have r equal cosine theta just sitting by itself? Well, we would really love to have r times cosine theta. But if we move the cosine over to the other side, we're going to have r secant theta. And that's not what we want. So options are to multiply both sides by cosine, and we would get r cosine theta, which we would know turns into x. But the right-hand side, we'd now have a cosine squared of theta. And that's a little trickier to deal with. Okay. So, of course, you could find a way to turn that into tangents by writing it as 1 over secant squared and then turning the secant squared into 1 plus tangent squared, and there you are. Now you found a way to convert everything to x's and y's. Again, there's a much easier way to deal with this, and that is multiplying both sides by r. Okay, so we're going to get r squared equals r cosine theta. And well, we know that r squared is x squared plus y squared, and r cosine theta is x. So we're going to get x squared plus y squared is equal to x. Okay, so, well, what shape is this? Well, x squared minus x plus y squared is equal to 0. Okay, so we know we're going to get some kind of a conic, but it's not evident what conic we're going to get. Why don't we complete the square here? X squared minus x So if we complete the square, let's add 1/4 to both sides. Plus y squared equals 1/4. And now we can factor this part right here to x minus 1/2 squared plus y squared is equal to 1/4. Okay. Aha. We can see that this is a circle of radius 1/2. And it's centered at 1/2, 0. Okay, so why don't we sketch that one on Desmos? Yes, Desmos does do polar graphs. So how do we graph in polar form? Well, you just start typing r in terms of theta. So I'm going to write r equals cosine of theta. Theta. Okay. And you can see that indeed this is a circle centered at 1/2, 0, and it has a radius of 1/2, just like we predicted. Okay. Now, for what it's worth, when you are graphing in polar form, it's actually a little bit nicer to use a polar grid in the background. And if you go into the options, you can choose a polar grid, and now this is a grid that's suited for plotting points in polar coordinates. All right. All right, and here we're going to convert Cartesian equations to polar form. So looking at part A, we have y equals 6. And we know that y is equal to r sine theta. So we can say r sine of theta is equal to 6. And while that is a correct answer, if possible, it's a good idea, it's a good practice to solve for r in the same way that with Cartesian equations, it's a good practice to solve for y if that's easy to do. So here, let's just isolate r. So we will get r is equal to 6 cosecant of theta. Okay. And for part B, we have x squared plus y squared plus 9x is equal to 0. Well, we know that x squared plus y squared is equal to r squared. And x is equal to r cosine theta. Okay, so this is our equation in polar form. Now let's see if we can isolate r. We can certainly factor r. We get r times r plus 9 cosine theta equaling 0. This splits into r equals 0, which is actually just a single point at the pole. But this part here is much more interesting. We get r plus 9 cosine theta equals 0. So r is equal to negative 9 cosine of theta. Okay. Now, how do we get both of these? Well, normally we'd have to say it's both of these independent equations, but actually we can just throw away the r equals 0 because it is a single point at the pole. And when theta is equal to pi over 2, this happens to go through the pole, right? So which means that it's redundant to say, hey, there's a point at the pole and there's also this particular other curve that happens to go through the pole. So we only need to present just this part of the solution. All right, so let's sketch these two equations. First one we'll sketch is the equation r equals 2. So this would be simply a sketch of all the points with an r value of 2. So that would actually just be the circle of radius 2. There we are. Okay, let's also sketch theta equals pi over 3. And that would be just every single point in the polar coordinate system with a theta value of pi over 3. So of course, in standard position, we know that all the points along there have a theta value of pi over 3.
But
So do the points this way. Now, of course, that's really 4 pi over 3. But remember, a point right here, for instance, this guy, could be a theta value of pi over 3 and a negative r value. In fact, this one would be negative 3 comma pi over 3. So theta equals an angle is a line through the origin, and r equals a number is just a circle centered at the origin. All right, let's sketch the equation r equals 2 cosine theta. So for this one, let's make a table of values here. Okay, so note that our independent variable here will be theta. Okay, so let's write down some of our favorite angles here, like 0, pi over 6, pi over 4, pi over 3, pi over 2. That'll at least get us through the first quadrant. And let's evaluate r. So r is 2 cosine theta. So r, when theta is 0, we're going to get 2. And then cosine of pi over 6, so we're going to get rad 3. Cosine of pi over 4 is rad 2 over 2. 2 of those is rad 2. And pi over 3, cosine of that is 1/2. 2 of those is 1. And cosine of pi over 2 is 0. 2 of those is 0. So these are 5 points. Let's go plot them. So the angle of 0, the angle of pi over 6, the angle of pi over 4, etc. We have evaluated r values for each of those. So it's going to tell us at each angle we're pointed at which r value to draw a dot at. So when theta is 0, r is 2, which means that there's our first dot. When theta is pi over 6, r is equal to rad 3. That's about 1.7. When theta is equal to pi over 4, r is equal to rad 2. That's about 1.4. When theta is equal to pi over 3, r is equal to exactly 1. And when theta is equal to pi over 2, r is equal to exactly 0. Okay, so what we have here is what appears to be the top half of a circle. And indeed, that is what that is. Okay. Now, let's continue thetas into the second quadrant. So 2 pi over 3. Okay. Followed by 3 pi over 4, 5 pi over 6, and finally pi. So when theta is equal to pi over 3, second quadrant angle, cosine of theta is negative 1/2. 2 of those is negative 1. And I'll just quickly do all of these evaluations. Okay, they're all negative because cosine is negative in the second quadrant. So now, when we're pointed in a direction of 2 pi over 3, which is this direction right here, r value is negative 1, which means actually we point ourselves this way and we move negative 1. So our next point is actually drawn right there in the fourth quadrant. When we point ourselves a direction of 3 pi over 4, our r value is negative root 2, which is about negative 1.4. So it's right here. When we point ourselves in a direction of 5 pi over 6, our r value is negative rad 3. It's about negative 1.7. Okay? And when we point ourselves in a direction of pi, our r value is negative 2, which is right here where we started. So actually this closes the circle. And indeed, this is a circle. And that is our graph. Okay, it will actually just repeat itself. If you don't believe me, let's just do something from the third quadrant here. The next would be 7 pi over 6. And the cosine of 7 pi over 6 is going to be negative rad 3. So here we are pointed at 7 pi over 6, and we would be evaluating a negative r value, which would get back over there again. Okay, so this is actually just a circle that goes around and around and around. So there's our final answer. All right, let's sketch r equals sine 2 theta. So let's just dive right in. What we're going to do is just walk through this guy by plugging in theta values 0, pi over 6, pi over 4, pi over 3, pi over 2, etc., all the way down around until we can get a really clear picture of what this thing looks like. So let's start with 0. So sine of 0 is 0, so we're going to start right at the origin here. Okay, now let's look at pi over 6. And we are doubling all these angles before taking the sine of them because our function is sine 2 theta. So this is really like sine of pi over 3, which is root 3 over 2. Okay. Now, a couple of comments. First of all, these numbers show up a lot, root 2 and root 3. And you should just know that root 2 is approximately equal to 1.4 and root 3 is approximately equal to 1.7. And that means that root 2 over 2 is approximately 0.7, and root 3 over 2 is approximately half of that. It's actually about 0.87. It's really 0.866 or something like that. So, okay. The other thing I want to point out is that the range of this function here, we know by its amplitude is going to be -1 to +1. Which means the entire graph is actually going to live inside that first concentric circle. But that seems like a waste of most of the space we have to work with. So I'm actually going to choose a scale so that 1 unit is 2 concentric circles. All right, so if we have to go out to 1 unit will be out here. Okay, we're allowed to do that. So, right, we started at the pole, because sine of 0 is 0. We considered pi over 6, and sine of pi over 3 is root 3 over 2, which is about 0.87. And that would mean that since half of this is 0.5, and there's 1, 0.87 is about here. Okay, so now I'm not going to draw the curve yet, not until we get a few more points. So, next angle we're looking at is pi over 4, which doubles to pi over 2, and sine of pi over 2 is 1. So we're going to put a 1 right there. Okay, and the next point we look at is pi over 3, right here, which doubles to 2 pi over 3, and sine of 2 pi over 3, second quadrant, still positive, is root 3 over 2, 0.87. So it's about right here. Okay, and next is pi over 2, and sine of 2 times pi over 2 is sine of pi is 0. So we're back at the origin here, which means that we started at the origin, we went through those 3 points and came back to the origin. Now, the whole time, theta was gradually increasing from 0 to pi over 2, which means that our curve is going to come out like this. It maximizes or peaks there and then comes in like this. Okay. Now, it's really important to get these angles into the origin and out of the origin correct. We evaluated this origin value right here at an angle of 0, so it's going to come out at an angle of 0. And we evaluated this origin value at an angle of pi over 2, so it's going to come in at an angle of pi over 2. So we wouldn't draw it coming out like this, say, right? Because that angle isn't coming out of the origin at 0 and coming in at pi over 2. That purple one that I just drew is coming out, it looks like, at pi over 6, coming in at pi over 3. So that's wrong. Okay, so where did we leave off? Well, we just had plugged in pi over 2, so our next thing to plug in is 2 pi over 3, which doubles to 4 pi over 3. And sine of 4 pi over 3 is negative rad 3 over 2. So while we're pointed in this direction, we're going to actually draw a point over here in the negative of that. Now we consider 3 pi over 4, which doubles to 3 pi over 2, and sine of 3 pi over 2 is negative 1. So while we're pointed in that direction, we actually are going to have a point negative 1 unit, so backward. And 5 pi over 6 right here, sine of double that is sine of 5 pi over 3, which is negative rad 3 over 2, and that's about here again. And finally at pi, we're just evaluating sine of 2 pi, which is 0. So we're back at the origin yet again. So remember, we came out of the origin at an angle of pi over 2. All right, so that's vertical. And then this guy comes in like this. And we had calculated that origin at an angle of pi. So it's coming in now kind of at an angle of pi. Okay, so now this is actually right where we left off at pi. Let's continue our quest. So now the next angle here is 7 pi over 6. And that doubles to 7 pi over 3, which 7 pi over 3 is actually a first quadrant angle. Sine of that would be root 3 over 2. So we're here again. And in fact, I'm actually going to just finish this thing because it would be too tedious for us just to sit and do all the calculations together, right? Hopefully you get the point of all of this. So it's going to come in, and then actually the last one's going to come out over here. These are actually fourth quadrant angles we're evaluating, but the R values will come out negative. Okay, and so we get this beautiful shape here. Okay, this is called the four-petaled rose. All right, very good. Okay, before moving on to any more graphs, I want to talk a little bit about symmetry. We're going to see that there's a lot of radial symmetry that emerges in these particular examples, and we should take advantage of that. So basically, if you have r of theta equaling r of negative theta, then the graph will be symmetric about the x-axis. Okay, and if you think of the visualization there, that's because if your r of theta is equal to r of negative theta, that means whatever happens this way will be matched this way. Okay, so you're going to get a reflection over the x-axis. So I want you to note that cosine of theta does satisfy this identity in general. So if you have a function consisting of cosine of theta or other stuff with a cosine of theta and no sines or anything, just cosine, then it will be symmetric about the x-axis because of this property. Okay, now what about symmetry about the y-axis? Well, that's if you have r of theta equaling r of pi minus theta. Then the graph will be symmetric about the y-axis. And the picture there is that if your theta is being read here as, of course, normal, pi minus theta will be reflected this way. And so you're going to get that symmetry on the other side. Okay, now, probably no surprise that analogous to the comment above, sine of theta does satisfy this property. So if you have a function consisting only of sine of thetas, you're guaranteed to have that particular symmetry. Okay. If you look at this sketch of 2 cosine theta that we made earlier, indeed it is symmetric over the x-axis. Okay. Okay, so based on the comment with respect to symmetry, for r equal 2 plus 2 cosine theta, we're going to expect this to be symmetric over the x-axis. Okay. So that's helpful. It means we really only need to investigate what happens between 0 and pi, the top half of sort of the unit circle, I guess, and the other half will be reflected perfectly. Another thing that we're going to do to this is we're actually, before we sketch it on our polar graph, we're going to sketch it on a set of r theta axes, okay, which means that we're going to give this like a traditional sketch, as if this were trigonometry class, okay? So what can we see here? Well, this guy has a period of 2 pi. It has a vertical shift of 2 units, and it has an amplitude of 2 units, which means the entire wave is going to live between 0 and 4 along the r-axis. Okay, and its baseline will be right here at the vertical shift value of 2. And being a cosine wave, we know that it's going to take on this particular shape for one characteristic period. Okay, so there's the classic trigonometry / pre-calculus class sketch of this function on r theta axes. All right, but what does this tell us? Just looking at it tells you several things. First of all, that your r values range from 0 to 4. That means that in this particular sketch, our r will never go negative. Okay, that means that if we're actually considering an angle in the third quadrant, r will be positive and our sketch will be drawn in the third quadrant. So that's great. It also tells us that our full range is only up to 4 concentric circles. Okay, so we can choose a scale so that this fits in our grid. And I'm actually going to just add a concentric circle to our grid so that we have 4. But we could also just condense it into the first 2. And finally, this tells us right here that our graph is going to make contact with the origin. R is going to hit 0 very briefly and only once in an entire cycle, okay? And that's right when theta is equal to pi. So, all right, I think we're ready to sketch this guy. So again, we're going to sketch it by simply consulting in order the different angle values and calculating using our function what r is. Okay, r here again is 2 plus 2 cosine theta. And plotting those points. So we'll start with theta equal to 0, and we see that r is equal to 4. Okay, and I'm actually going to put that right out here. Now, I'm going to skip ahead to pi over 2, because we can see from our graph above that at theta equal to pi over 2, r is equal to 2 units. Okay, and as theta increases from 0 to pi over 2, our r values gradually decrease from 4 to 2, which means that the entire curve is going to be some gradual transition from that first dot to that second dot. And let's actually plug in the individuals here. So let's plug in pi over 6. Okay, cosine of pi over 6 is root 3 over 2. So our r value here is going to be 2 plus root 3. Okay. So remember, root 3 is about 1.7. So this is going to come out to about 3.7. So there's 3 right here, and 3.7 is about there. Okay, now we'll try pi over 4, and cosine of pi over 4 is root 2 over 2, so this is 2 plus root 2, and again, root 2 is 1.4, so this is about 3.4. Okay, and now let's check pi over 3. Cosine of pi over 3 is 1/2, so this is like 2 plus 1, which is 3, so that's actually right there. Okay, and what we're going to get is, we can see exactly how bulbous this is. It's like that. Okay, and let's continue our mission here. At 2 pi over 3, we can see that our cosine values will be negative. Cosine of 2 pi over 3 is negative 1/2, so this can be 2 minus 1, which is positive 1. So it'll be right here. Okay, so we've dramatically started shrinking, and as we know, as we approach pi, this is going to eventually arrive at the origin. Okay, so next is 3 pi over 4, and cosine of 3 pi over 4 is root 2 over 2, so this is like, well, negative root 2 over 2, so this is like 2 minus root 2. That's about 0.6. Okay, and finally, for a moment, we have 5 pi over 6, and cosine of that will be negative rad 3 over 2, so this is like 2 minus rad 3, and that's about 0.3. And then, of course, at pi, we get 0. So this thing's going to come in along this trajectory, and it's actually going to come in to the pole here perfectly flat, because it's coming in at an angle of pi. Okay. And by the symmetry of cosine here, we know this is going to be reflected along the other side. So actually, all we have to do is just put those, it's going to come out again flat, and we put those same points. Let's just put some of the main ones here. It was kind of like that, and then like that. Okay, and that's the shape that we get. And this shape here is called a cardioid. So it's like a heart. Very nice. So math is now full of flowers and hearts. It's a very romantic subject. Okay, let's sketch this guy now. So we're going to start the same way we started the last one, which is by sketching this on r theta axes and seeing what it looks like in classic Cartesian coordinate mode. So we can see, again, we are going to have a period of 2 pi. Okay, here we're going to have a vertical shift of 1 unit. So our baseline's right here. And an amplitude of root 2. So that's about 1.4. So from the baseline, we'll go up about 1.4 units. So there's 1 plus root 2. And we're also going to go down about 1.4 units. So that gets us just a hairline below the theta axis. And let's draw our sine curve. Okay, again, we know from trigonometry that it takes on this shape, like so. So our range of r values here is negative about 0.4 and up to 1 plus root 2, which is about 2.4. Okay. We can also see that for the most part, our r values are positive, except between here and here, our r values are negative. Okay. So for a small part of our graph, we're going to actually be drawing on the opposite side of whatever theta values we're investigating. But for most of it, we're going to be drawing on the side that we're investigating. Okay. So let's go in and sketch this guy. So at theta equals 0, we get sine of 0, which is 0, so r is equal to 1. So we'll put a dot right there. At pi over 6, we get 1 plus root 2 over 2. Remember, root 2 over 2 is about 0.7, so this is 1.7. Okay, let's put it right there. At pi over 4, we get 1 plus 1, which is 2. Okay. At pi over 3, we get 1 plus root 2 times root 3 over 2, so that's root 6 over 2. Okay, so square root of 6 is a little over 2, so this is a little bit over 2 points. So let's call this like 2.3. It's about there. Okay. And finally, for a moment, at pi over 2, sine of pi over 2 is 1, so we're going to get 1 plus root 2, which is about 2.4. Also, we're going to have symmetry on this side because of the fact that it's a sine function in there. We're expecting exactly the same values. So far, what we have here is sort of an alien head here. And let's continue on sketching these ones here in the third quadrant. So 7 pi over 6. Okay, so sine of 7 pi over 6 is negative 1/2. So this is like 1 minus root 2 over 2. Okay, so that's about 0.3. And at 5 pi over 4, sine of 5 pi over 4 is negative rad 2 over 2. So this is like 1 minus 1, which is 0. So actually, we're right there at the 0. In fact, now we know that 0 occurs at 5 pi over 4. Okay. But we're not done the third quadrant. At 2 pi, or pardon me, at 4 pi over 3, sine of 4 pi over 3 is negative root 3 over 2. So we have 1 minus root 6 over 2. So again, the square root of 6 is something a little over 2. So half of that. So this is a small negative number, and it's going to be right about there. Okay. At 3 pi over 2, sine of 3 pi over 2 is negative 1. So we're going to have, at this part, 1 minus root 2, which is 1 minus 1.4. Okay, that's about negative 0.6. And we know that this is going to reflect this way and close itself off like that. Okay, and in fact, this is indeed the shape of our graph. This is called a limison. It's French for snail. Now you probably know 2 words for snail in French. So there we are. So that loop of the limison is this negative part right here. Okay. If it actually dips below the axis, meaning the amplitude is greater than the vertical shift of the function, then you're going to have a loop of the limison. Okay, so there we go.